Okay, let's start back up, and this is lecture number 3. So I'm going to go through part of lecture 3, and then we're going to have a break for an hour or so to do assignment number 1, or activity number 1. And then we're going to have another little part of this, continuation of lecture 3, and then we're going to break again to do assignment number 2. So it's going to go every other, kind of break things up a little bit. So if you can just be seated for an hour or less, I guarantee it will. Then we'll be starting to work on those assignments. And so it's okay. So I got my clock here, so I'm ready to go. So hello. I'm sorry. I just don't want to yell over you. Hello. Okay. Just wait for everybody to be quiet. All right. So this is what we covered before lunch, if you remember. We talked about different types of agents. We talked about rational and what it meant to be rational or irrational in terms of rational actions, and we defined the Turing test and we defined the definition of AI. So now what we're going to do is look at our first approach, which is really chapter, believe it or not, 3 of the book, and it's called searching. So searching algorithms. So the problem solving in terms of coming up with a search to find a solution for solving a problem. So what we're going to look at then is the introduction to problem solving as a concept, and the concept of searching. So I'm just going to cover problem solving right now. And then after we do a little break and we do the exercise, then I'm going into the concept of searching, because we have different types of searching that we do in AI that I'm going to be covering. So I'll also look at the concept of complexity before this lecture is over with, uniform searching, and informed and uninformed searching, by the way, not uniform. So the problem formation, the heuristics, the way we come around solving the problem through searching algorithms. So let's talk about problem solving. So here's your introduction to problem solving. Hello? Okay, so here's an example. It's a measuring problem. It's a very easy problem to solve, actually. In fact, by looking at this, if I look at the problem, it says, using these 3 buckets, measure 7 liters of water. I have one bucket that has 3 liters, one bucket that has 5 liters, one bucket that has 9 liters, and I want to start solving the problem. Not always going to be this simple. In fact, if it was this simple, I would not be writing an artificially intelligent solution to this, because it would not take any artificial anything. Actually, it doesn't really take that much intelligence either. Because if I had 7 liters, I'd probably pick this bucket here that said 9 on it and fill it up with 7 liters of water, because I know it's going to fit in that bucket. But what if we don't know and the problem space is bigger? So this is the problem space. It's the environment for which we're considering a solution. Problem is defined by 3 buckets. What if I had 3 million buckets? A little bit more complicated. So what if I didn't know maybe how many each bucket held? That would also be a problem. So this is very simplified to demonstrate the problem-solving approach. So the first thing we do is we come up with possible solutions, which is what we're doing in troubleshooting for most of the time. In fact, when you look at the Rubik's Cube as an example, which is another problem solving, the space on that's a bit bigger than the bucket problem here, or the Tower of Harmony, or whatever it's called. You take the pins and you go from one pin to another pin, and they have to put the plates on top of each other so that the big one's on the bottom. That's another problem-solving approach, another problem itself. But in terms of the measuring problem, we usually go through the possible solutions. Solution number 1 would be to start in some particular order, like maybe left to right. And it's a searching problem, but it's also, kind of a good example of problem-solving techniques. So in terms of one possibility, we would start out and we would have no water in A, B, or C. And then we would start with A, and we'd fill up bucket A with 3 liters, and we go, oh, that's as high as it goes. We can't go any higher. So then we go, okay, what about the next one? We could start out and skip A and go to C, and put 3 liters in there. We take those 3 liters and move them over to the 9-liter bucket. Or we can say, okay, now we have 3 and 3, because we took the water, we put it in the 3rd bucket, we took the 3rd bucket, we dumped it in the 9 bucket, because we were trying to fill it up all in one bucket. So we decided, okay, let's just start from the left and move to the right in terms of the sequence. And then we take the 3 from the A, we dumped it into the 9-liter bucket, so now we have 6 over there in the 9-liter bucket, and then we go back and say, okay, let's fill it up again. This is using bucket A to fill it up, to transport from bucket A to bucket C, and so now we have 6 over there, And then now we take them, let's say we started with B, and we say, oh, give it another 3, and we have 6. And then eventually we have 3 and 3, we fill it up, and 5 and 1. And eventually we're going to get down to 7 liters because we have an odd number of bucket, and this is a 3, a 5, and a 9. We started with the second B bucket to kind of pick up a little bit of the extra volume that we needed. Not such a good solution, but it works. It is a solution. Not what I'd call an effective solution. Because if we took another alternative solution here and start with bucket B, so instead of starting with A, we're starting with B, and we're going to fill up B, and then we're going to basically do a similar process. I'm not going to go through it step by step, but I'll just kind of go to the end. You see there's fewer number of steps that we have to get to in order to reach the goal of having 7 over into the big bucket. So which one do you prefer? Probably solution number 2. How did you get to solution number 2? I have no idea. Just randomly selected A, randomly selected B. That's a search, by the way. We're only searching among 3 different possible solutions. We could start with A, start with B, start with C. If we started with C, we reversed the search. That makes it artificially intelligent because we're now starting with the logic of we got a bucket that's going to hold it all. We can just load it up, put 7. We can put 7 in a 9-gallon bucket, so we don't have to search. But maybe we don't know ahead of time how much each one of them holds. Also, how do we know we're going to start left to right versus right to left? So some of it's guesswork, not very artificially intelligent, because intelligence and guessing are 2 separate things. So the solution in this particular case didn't come out on our first try. It may not come out in an artificial intelligence environment either. So what we do is we come up with this problem-solving agent. We call it an agent because this is the agent who's going to solve our problems for us. So we take the inputs, we define the environment space, and then we come up with a bunch of formulas or pseudocode or problem-solving approach. So this is what's referred to as offline problem-solving. Online problem-solving involves acting without complete knowledge of the problem in the environment. So if we were to do it offline, we would first take and measure each one of the buckets, and then we would know which one to start with. And then we'd know if we didn't have one that was big enough, we would find a combination. So you come up with the answer before you actually start implementing the solution. An online solution is when it happens in real time normally, which we don't normally get any control over. It just happens, and then we're dealing with the solution while we're finding it. Network attacks and network sniffing software and control, security access control and stuff is definitely an online solution. Every time the user puts their password in, if they do it 2 times, 3 times, lock them out. It could also be set algorithm in the system. So there's a kind of a fine line between what's the difference between implementing an algorithm and implementing an intelligent agent. Well, an algorithm is going to do a systematic, inefficient solution to the problem. If you've taken an algorithms course, we have running times of especially searching and sorting. Different techniques lend themselves to different running times or efficiencies. As an example, the difference between a linear search or start at one list and go to the end versus a binary search is an example. A binary search can be much faster. But binary search is an offline problem solving. Linear search is an online problem solving because we have to take in order to apply a binary search to a list, we have to organize the list in alphabetical order or numerical order somehow. Well, that means we have to go through and read the data, understand the environment, then organize the environment. So artificial intelligence is the same kind of concept in terms of efficiency between the differences between running an ordinary algorithm and then running a binary approach to it, a more efficient algorithm. So in an artificial intelligence solution, we're not adding efficiency, we're adding logic, and we're adding intelligence to the solution. So it might be in the form of creating a genetic algorithm. In fact, that's what you're going to do for one of your assignments. And I'm going to go through genetic algorithms probably tomorrow, or maybe Sunday at the latest. Genetic algorithms sounds like really complicated, but it really isn't. It's actually pretty easy. And looking through and modifying searching and sorting, but not doing it in a traditional computer science fashion. So in the example of sorting, putting weights on sort criteria and using a tree to sort something. So you have like a Bayesian network where you've got like certain areas are going to be higher likely for the solution, and you're going to be able to see those certain areas depending upon the weight and the way the tree is being built. So you can actually analyze the data while the data is being analyzed in that kind of a fashion. Versus searching, where you're going to start with an informed decision. You're going to measure the buckets. You're going to do something to give yourself a starting advantage, which is what is intelligent about the concept. So artificial intelligence is not applying traditional algorithms to traditional problem solving. It's changing the algorithms to make them more intelligent and changing the problem solving approach to making it a problem solving that's appropriate for AI. So there's a lot of people who don't take AI classes or don't study AI, they go, it's just a matter of putting a search algorithm on there. Or it's just a sorting, or it's just a, nah. There's supposed to be an intelligent approach to it. It's a different philosophy. Someone's talking in the back. Don't know who it is, but it's bothering me. Thank you. It stopped. Okay, so here's the example of the buckets. And actually there's a room back there you can walk in. I don't know who was talking, but oh, he's on the phone. Hey, excuse me, you can take the phone in that room back there, or you can take it outside. Thank you. So let's see, we got different types of examples here in terms of the buckets. We can measure 7 liters of the water using the 3-liter bucket, the 5-liter bucket, or the 9-liter bucket. So this is a way of formatting the solution, because I'm talking about developing problem solutions, and I'm going to ask you to develop a problem solution. So this are some of the things to think about in terms of your development. Every single solution has a goal. If you leave the goal out, you're not attacking an AI problem. So the goal is going to be the formulaic goal. Have 7 liters of water in a 9-liter bucket. That's the goal. The formula or the formate problem itself is the states, the amount of water in each one of the buckets, and the operators are to fill the buckets from the source and then empty the bucket. So fill the bucket and then empty the bucket if you need more. So that's why you fill up the 3-liter bucket and you empty it into the 7-liter bucket. Seems inefficient, but people do this in their lives actually. It's like somehow like people they work towards something and then let's just do it again. And then they figure, well, if I just took all that stuff and applied it this way, it'd be done faster. If you ever watch anyone organize a closet or organize a garage or do any kind of task in which you have to think and you haven't thought ahead, and you make piles and then the piles get moved into other piles and those piles get moved into other piles, and you think if you just stopped, made an informed kind of an analysis and did it offline and just looked the whole picture and mapped it out ahead of time, it's kind of like building those IKEA things. There's some people that just open up the box and just start putting them together in different combinations, and then they have extra pieces left over. And then there's the other people that say, all right, I'm going to do this offline. You read the instructions. You take all the pieces from the box. This is me. You put them in different piles. And then you go, okay, a half hour, 45 minutes later, after the person I'm building this with is bugging me, oh, are we going to start doing this now? Like, yes, we're going to start doing it now. We're going to start doing it right now. After I've got an informed environment and I know what I'm working with. And then it comes together and it's much better product in the end. And it doesn't take as long either. It's kind of like software engineering, actually. People don't like to write requirement docs and analysis and design documentation because it's like 2 or 3 weeks or a month or 2 before they start writing the software. People just open up their computer, okay, let's just start writing the software. Yeah, but it's not informed. I call it informed. It's really offline thinking, and it's something that's crucial to artificial intelligence solutions. It's the thought before the thought. So remember back to an environment types. It was given in lecture number 2. So to solve this sort of problem, you have the formulating of the goal, the problem, finding the solution, and you have the environment that you have to consider. If you don't consider the environment, you're not working with an informed way of going about the solution. It's largely determined by the agent design. So we have problem types, just like we had agent types. Single state problems, multiple state problems, contingency problems, and exploration problems. So a single state problem type falls into the deterministic accessibility category. And then we have multiple states, which is deterministic and inaccessible. So these little quadrants here, accessibility and deterministic and accessibility, they come in different combinations. They give us our different problem types. So in a single state, the agent knows everything about the world, thus can calculate an optimal action sequence to reach each goal state. And there's only a single state. The buckets could be considered a single state if the agent took some time to inform themselves about the bucket quantities. Then that would have been a really simple single state problem. Multiple states, agent must reason about the sequence of the actions and the states assumed while working towards the goal. So the car that's avoiding obstacles is a multiple state. So it's kind of like what we do in a car, as an example. When we hit, we're going down the freeway at 100 miles per hour and we hit dead stop traffic and we have to slam on the brakes. And you have to decide, if I go to the right and I hit that car, it's going to push that car into that other car and it's going to smash my right side of the car. Or I've got the left side of the car I can be concerned with, and I can go to the left. Or I can just slam right into the back end of the person in front of me. Or I could slow down and hope and pray that I'm going to make it in time before I hit anything. So it's kind of like, the car going around the track. I can hit the man, I can hit the cone, or I can hit the bleachers. Well, chances are you're not going to hit the bleachers. So if you just head off in the X area of the bleachers, you're probably going to run over a small child or something. Who knows? What other things you're going to encounter. But one leads to another, which leads to another. And they call it the domino effect, where you have multiple states you have to consider. And what you have to do in this particular problem scenario is the intelligent agent has to look ahead into the future. So it's like you as a college student, if you were younger in your career, and you say, well, if I study computer science now as an undergrad, then I can go to ITU and take computer science courses as a graduate student, and then I can study AI or something like that. Or you can think, well, I really like healthcare. But if you're a healthcare student, likelihood of you taking this class is kind of slim. So if that was the goal, then you're never going to get there. So it's your sequence event in your planning, which is the multiple state. Then we also have the contingency problem. So I run over the guy. Okay, now what do I do? Step on the gas and go as fast as I can in the opposite direction and pretend like it wasn't me. So your contingency plan. What happens if I fail this class? I take it again. So yeah, it must have sensors. So contingency problem must use sensors during the execution of the option. So you have to be able to identify what happened. And the solution is a tree or a policy that's going to be enforced. And often interleaved with searching and execution. So you're going to have to search again for another solution as a contingency to the first solution that you created. And it's not an avoidance, so you don't have to have contingency. Contingency happens as a side effect with multiple state problems. So some of these things actually work together. And then we have the exploration problem. That's what we just did a few minutes ago with the buckets. We have unknown state space. We don't know what's going on. We're exploring for different opportunities to see what we can find. So we discover and learn about the environment while taking actions. Then we go, oh, don't use that 3-liter bucket for anything. It's not worth it. But if we only had 1 liter and we started out with the 3-liter bucket, we'd be done. There's no need to waste time looking at all of the other buckets. So sometimes the exploration can quickly find a solution where if you did an informed search, then it's going to take you a lot longer. It's kind of like if you had a binary search and you're applying a binary search to 10 items, probably going to take you longer than if you did a linear search on those 10 items because it's easier. You don't have that wasted time in the beginning to sort those 10 items. So this is the example that's actually in your textbook. It's the vacuum world. So it's a simplified world. There's 2 locations. Each may or may not contain dirt, and each may or may not contain a vacuum cleaning agent. So the agent in this example is the vacuum cleaner, and the vacuum cleaner's goal is to pick up the dirt. So if it's a single state solution, you would start in cell number 5 here. It would not be a good solution for a single state because, well, actually it is. You just go to the second part and you pick up the dirt, because you have both the vacuum cleaner and dirt, but they're in 2 separate spaces. So they're in adjacent cells, however, which makes it pretty easy. Or a multiple state solution to this problem might be start in any one of these areas and then go to any one of these other areas, because you're bound to hit from multiple states. If you go into an area, like if you start here with 1, you're going to pick up dirt, 2, you're going to pick up dirt, 3, you're going to pick up dirt, 4, you're essentially going to be rotating. Or contingency, you start in number 5, and then Murphy's Law can dirty a clean carpet. So if you're in 5 and you go, well, if we just suck it up, maybe we'll find dirt there, which is the contingency that says just if the vacuum has 3 states, a suck, a start, and a stop, then if you start and you suck and there's nothing there, well, this is that joke. It's actually a joke, Murphy's Law. It says, if it's going to break, if it's not broke, or I don't know Murphy's Law. I haven't heard Murphy's Law in years, but if you look it up, Google it if you're bored on the internet, go Murphy's Law. It makes no sense usually, but say that one more time.
Something is about to go wrong.
If it's going to go wrong, it's going to go wrong. If it's about to go wrong, Murphy's Law says that expect the unexpected. So even though there's no dirt there, there'll be dirt there. So the vacuum cleaner itself is going to make some dirt. Well, every time you turn on a vacuum, it makes dirt anyway. So it's like a car. If it's going to leak oil, you're going to turn it on. It's going to leak oil right there. So you should turn it on. Local sensing. So we can have dirt location only. We can local sense it, and then we'll have an informed decision that says if we're in number 5 and we don't have any dirt, don't turn the sucking on. Move to another location. And that would give us a location sense. Where's the dirt? So we have this thing called the traveling salesperson algorithm that everyone learns as a computer science student. And I'm going to assume that you guys have heard of computer science. So some of you do come from business backgrounds. That's why I have to say that. This is an international European version of the traveling salesperson algorithm. Traveling salesperson algorithm, if you haven't heard it before, is one of the most complicated algorithms to solve. In fact, it doesn't lend itself very well to efficiency because the scenario is you got a guy who's got a briefcase full of product and he's trying to sell it. And he's going door to door and he wants to hit as many houses as possible and cover the most amount of city that he can in one day so he can make the most amount of money. So he's trying to plan out his routes because the route's not even. It's not like he can go in a systematic order. The streets don't all connect. There's dead ends. There's, loops. And it's a neighborhood. So the algorithm says, how do I get from point A to point B and cover the entire span in the least amount of time? Which is very similar to mapping and GPS problem solving. When you go and you turn on your TomTom and you type in the address and you go, or your Garmin or whatever you have, and you say, I want to get to this address. Well, it sits there for a few minutes and it calculates. Notice it doesn't come back instantly. And usually comes back with a couple of different options, and the options that it gives you are the times. It says, well, we can take all freeways, and it's going to take us 10 minutes. Or city streets, you like this route, you like that route? Because it's not too intelligent. It's not going to pick the best route. However, there are machines, GPS machines, that are intelligent. They pick up the traffic information, and you put in intelligent routing. That's what they call it. Some of them call it intelligent routing. Takes the traffic conditions into consideration, and then it alters your route, given all this intelligent information it has about the current state of your travel plans. And it will tell you what the better route is, because one route might take an hour, and the other route's going to take 5 minutes, depending upon. And then so it's a little bit better gamble in terms of the time it's going to take you. In this particular example, it's Romania. And in Romania, on vacation, you're currently in Arad, and you have to fly out of Bucharest tomorrow morning, but you're in the wrong city, so you need to get to the right city so you can catch your flight in the morning. So you have formulated a goal. You want to be in Bucharest, if I'm saying that right. And the formulated problem states you have various cities in between here, between point A and point B, and you need to decide how you're going to travel through these cities so that you can get to your final destination so you can make your flight the next morning. Because for some strange reason you didn't plan your vacation out correctly. You did the exploration technique, problem solving, because you want to hit all the cities, so you just explored through randomly to see what you would hit without a plan. So to find a solution, you're going to look at the sequence of cities such that the total driving distance is minimized. And you want to get there as soon as possible. So you have your route, and you map it out. Here is point A, and here is point B. So the computer scientist would say, well, this is a tree solution. Could be a tree solution. It could be a searching tree solution, because we can take a look at the problem formation, and we can outline it, and it does lend itself quite nicely to a tree. However, in assignment number 2 of your take-home assignments between now and the next class meeting, you're going to use a genetic algorithm to solve this problem. And you're thinking, what's it? Don't worry about the word genetic. Don't let that scare you. It has nothing to do with biology, or has nothing to do. It's just another technique that you're going to learn. It's very simple, actually. So when you're all done, you can say, "Hey, we practiced genetic algorithms in this class." Well, you are, actually, in a simplified format. But let me compare the two after I tell you what the tree solution is going to look like. It's a search tree. So here's the problem. So it's defined by 4 cities. The initial state, 4 items, excuse me. The initial state, the operators, the goal test, and the path cost. Because we really need to know what we're comparing in order to know which route is going to be the best, because we're trying to pick the best route. So in the initial state, we're at this city. The goal test is, can we be at this other city? And can we be there explicitly, or in terms of the vacuum cleaner problem, this is kind of putting both together at the same scenario. There's no dirt, which means we're going to be able to pick up everything in all the different rooms, and we're not going to have any dirt at the end, which is the same kind of search solution as this tree for the starting and ending location. The operators are the successor functions. If we go to this city, then we have to go to this city. As an example, if we go here, then we might have to go here, or we might have to go here. And we see if we have multiple options to get to the same location. And the path costs. So it's basically adding up the distances between the cities. So sum of the distances, the number of operators executed. So and here we have the solution, which is a sequence of operators leading to the initial state of the goal state. So then we selecting a state space. So then we're defining the spaces. So the real world is absurdly complex. So some abstraction is necessary to allow us to reason with it. Okay, so our state space is just going to have what city are we in, what city is next, not considering any other options or any other information. So selecting the correct abstraction and resulting state space is a difficult problem. If you think about the concept, this one's pretty simple. If you wanted to get from point A to point B, and we wanted to make this a little bit more realistic, we could fly, we could drive, we could walk, we could skateboard. We could have all of these different options that we might be able to take. One of them is going to yield a smaller distance. So we're not doing that. We're just looking at the cities, and we're simplifying this problem solution. The abstract states are the real world states that we could possibly relate to this, and abstract operators are the sequence of real world actions. So as a combination, we could drive. In fact, some people find that when they go to San Francisco and they take public transportation, it's easier to drive and take public transportation. And for me, a few minutes ago, I spent 11 minutes, according to my GPS, walking to somewhere where it would have taken me 25 minutes to drive and park. And I did it in 11 minutes because I looked at it ahead of time and I Googled it, and I said, well, okay, driving, walking, it's easier to walk. Plus, I get a mile's worth of exercise today because it was a half a mile each way. So that means I can eat an extra cookie or something later on this afternoon. That's my artificially intelligent reasoning system. All right, so the abstract solution says it's a set of real-world actions to take in the real world, such as to solve the problem. So this is the goal-based agent who's working through a search space and defining the model for the solution. And what I'm talking about is problem solving, by the way, just to regroup here. I'm not talking about the algorithms or the paths through a network, whether it be a genetic algorithm or whether it be a tree algorithm or anything that we have to do with this. So let's talk about another one. Let's talk about the 8 puzzle. So we have a starting position and then we have a goal position. And so look at this. We have state, operators, goal test, path cost. So if I tell you in a midterm exam, or if I tell you in a final exam, or if I tell you in a homework assignment, you're going to get it in a homework assignment. It says, create a problem solution that identifies the agent behavior and provides a reasonable solution to the problem of getting from point A to point B. This is some of the stuff you'd figure out. Or taking this state and putting it into that state. It's all the same thing. It's all the same problem solving. So you have an initial state and you have a destination or a goal state. And you have the environment, you have the states, the operators, and the goal test. The goal test is really going to be your algorithm. And then you have your path cost. So you can compare all your different options, just like we did with the buckets, actually, to kind of see, well, which one's going to yield us our best results. So if we look at this one, and their state would be the initial location of the tiles, ignoring any intermediate locations. But where's our starting point? Our tiles look like this. What's our ending point? It's supposed to be looking like this. This is sort of in order. Operators, well, we can move blink left, right, up, and down, ignoring the jumping. So we can, you know those little games, you put your finger on the tiles and you move it up. Back to, there's one for the iPad, actually, it's pretty cool. And does the state match the goal state in terms of the goal test? So every time you make a move, you have to calculate all the other moves ahead of it and say, is this going to lead us anywhere closer to the goal? Because this is a goal agent. And go, yeah, it does. Okay, then that's the correct one. So it's a multi-state changing environment. And then the path cost is 1 per move. So we counted at 1 per move, how many times it's going to take us to move those pieces. So why a searching algorithm? We have 8 puzzles, which has 362,800 states. 15-piece puzzle is going to have more, and it just gets complex. So we need a principled way to look at the solution for these huge search spaces, which is why traditional algorithms don't necessarily work correctly, but an artificially intelligent enhanced searching algorithm might, actually, especially if you reduce that problem space down. Here's that vacuum cleaner again, in vacuum world. So if we take and look and we frame this out, what do we have in terms of the states? Well, the integer dirt and robot locations. Ignore the dirt amounts. Just say there's dirt, then it's a 1. If there's no dirt, then it's a 0. Kind of an on-off kind of thing. The operators are a left, a right, or a suck. Move left, move right, or suck. And the goal test is that there's no dirts at the end, which is where we're going to get to the end. And 1 per operator for the path cost. Every time we move the vacuum, it's going to cost us one ratio, or 1 speed that we're going to work with. We can apply this to a robot assembly as well. So you can apply this to any problem scenario. So in terms of the state, the real valued coordinates of the robot joint angles and the parts of the object to be assembled are going to be the states. The operators are going to be the continuous motion of the robot joints. The goal test, is it going to be completely assembled with no robot included? So it's going to be completely assembled. Or is there a, the path is going to be the time it takes to actually execute all of the different steps. Put this into a real-life design. VLSI Layout as an example. So given a schematic drawing comprising components of chips, resistors, capacitors, etc., and interconnections or wires, find the optimal way to place the components on the printed circuit boards under constraints that only a small number of layers are available because you want to minimize costs. And wires wires on a given layer cannot cross. So we want to make it so we reduce the number of layers on the board. And we've reduced essentially the amount of space on each one of the layers, and the wires aren't crossing. So we have a kind of an easy, kind of an optimal way of doing it. Well, we minimize the search space, minimize the number of layers, minimize the number, and these are essentially the criteria that we're looking at. And minimize the number of vias, connections between one layer and another, minimize the length of such signal layers at the clock line, and distribute the heat throughout the board. You don't want the board to overheat. Certain components make up more room. So there's actually artificially intelligent programs that do this stuff, the VLSI design of boards that rearrange things in different configurations that you would not have even thought of, probably. So, not to say that this is a simplified concept, it's actually quite advanced, but there's design theories that say, okay, make this into one board. Take out all the layers and put it on one board. Well, the board's going to be pretty big. All right, put it into multiple layers. The board's going to be smaller. But then you have to have insulation and you have to have other things. So it would have worried about the thickness, and then it gets more expensive. Certain designs are a little bit more expensive than others. So it's basically a way of putting the drawing in, and then put the schematic in there and say, okay, give me all the different options I have. And artificially, you can actually, using all the logic, put together the components in a design, and then the board would have a layout that looked like this. This is a little carrier board example. And you'd be able to see it in a three-dimensional model and some of these. And this is artificial. It's not what I'd call a sophisticated artificial. It's an automation application that's used. In fact, you can do this with a lot of 3D modeling tools as well. CAD programs allow you to do that. Some functionality that's borderlines on artificial intelligence. But it's problem solving. And comes into the case in which you have to come up with a design. And someone picked the design for a reason. Well, you have criteria, which is why you're doing that. So this is where I'm going to stop for this lecture, so you guys can all wake up now. I'm going to stop the lecture, and I'm going to talk about the first in-class activity that you're going to do. So I'm going to leave it on slide number 40 and take a look at what you're going to do next. So I'm actually going to stop this video here.